It is recommended that to watch this video in high picture quality. In today's video, we'll be discussing about Chemistry Paper 2 AS Level Structured Question 2024 February-March Variant Test 22. Question number 1. Bismuth is an element in group 15 of the periodic table. Bismuth has metallic bonding. Draw a label diagram to show the metallic bonding in bismuth. So, since it is metallic bonding, so positive ions surrounded by delocalized electrons is the structure. Then, in part B, bismuth reduces water to form bismuth oxide, a colorless gas that ignites with a squeaky pop forms. Pop also forms. Since pop sound is formed, that means hydrogen is released. And consider the equation for the reduction of water by bismuth. So what is the equation? So bismuth reacts with water. So bismuth reacts with water from bismuth oxide, that is bismuth oxide, and since pop sound is formed, so hydrogen is also released, and then we need to balance this. Then in part 2, deduce the structure and bonding in bismuth oxide. Explain your answer. So what is the structure and bonding? Bismuth oxide is a yellow insoluble solid that melts at 1090 Kelvin. So this is a high temperature. Then the molten compound conducts electricity. Since the molten compound conducts electricity, so it must be an ionic compound. So it has giant ionic structure with strong electrostatic forces of attraction between positive and negative ions. And as it conducts electricity, so we can also write this as it also conducts electricity when it is in molten or in aqueous form. So giant ionic structure which is strong electrostatic forces of attraction between positive ions and negative ions, and it also conducts electricity when it is molten or in aqueous form. Part C. Bismuth oxide can be used to form NaBiO3 as shown in equation 1. So this is the equation 1, and bismuth oxide is used to form NaBiO3. Deduce the oxidation number of bismuth in BiO3 and NaBiO3. So what is the oxidation number? So for BiO3, as there is 2 bismuth, so we consider bismuth as a X, or its oxidation number as X, and oxidation state of oxygen is -2, and there is 3 oxygen. After calculating, we get a value that is 3, so it is +3. Then for NaBiO3, the oxidation state of sodium is +1, and for oxygen it is -2, and since there is 3 oxygen, so it is multiplied with 3. After calculating, we get a value that is +5. Then identify the reducing agent in equation 1. So reducing agent is a substance that causes another substance to be reduced, and the reducing agent itself is oxidized. So here we can see that bismuth oxide is oxidized as its oxidation state increases from +3 to +5. Therefore it is a reducing agent. So bismuth oxide is a reducing agent, and you can avoid this. NaBiO3 is an oxidizing agent with similar properties to KMnO4. So KMnO4 is an oxidizing agent, and it is also an oxidizing agent. Figure 1.1 shows an example of the use of NaBiO3 as an oxidizing agent. So this is the NaBiO3, and it is acting as an oxidizing agent. So first of all, X is a diol. Then diol is converted to a ketone, that is CO group, and an aldehyde, COH group. Then explain the term oxidizing agent. So oxidizing agent is a substance that causes the oxidation of another substance, and the oxidizing agent itself is reduced. So a substance or a species that causes the oxidation of another substance, and itself it is reduced. In part 2, compound X forms when methylbutene reacts with KMnO4. So when methylbutene reacts with KMnO4, compound X is formed. So state the essential condition for this reaction. So first of all, for methylbutene, since it is butene, so it must contain 4 carbon atoms, that is METH, ETH, prop, but. So butene, and as there is 2, so the double bond is between second and third carbon atom, and as there is methyl group present, so we just added a methyl group. So methylbutene reacts with KMnO4 to form X. So this is the structure of X, that is C, carbon is attached to two methyl groups and one OH group, that is two methyl groups. Then this carbon is attached to one hydrogen, one OH group and one methyl group. So here if we compare, then we can see that the rest of the structure remains the same, just the double bond breaks and two OH groups are attached. Since two OH groups are attached, so it is cold diluted acidified KMnO4. And if it is hot concentrated acidified KMnO4, then the double bond breaks, and since this carbon atom contains two methyl groups, so this is converted to ketone, and since this carbon atom is attached to one methyl group and one hydrogen, so it is converted to aldehyde, and on further oxidation it would convert to carboxylic acid. In part 3, complete table 1.1 to show what is observed when compounds Y and Z react separately with the named reagents. So reagent, observation with Y and observation with Z. So for Y it is a ketone, and for Z it is an aldehyde, that is COH group is present. Then for Na2CO3, for the reaction with Y, there would be no reaction since ketone does not react with Na2CO3, NaOH or sodium. Ketone does not react with any of the substances. And for Z, Z is an aldehyde, and aldehyde also does not react with any of these three substances. So you must remember that for aldehyde and for ketone, they does not react with Na2CO3, NaOH and sodium metal. So there would be no reaction. Then with alkaline aquacidin will react with methyl ketone or with methyl hydroxyl group, that is methyl ketone or with methyl hydroxyl group. But you must remember that alkaline aquacidin does not react with ethanoic acid, that is CH3COOH group. So since it is ethanoic acid and it is not methyl ketone or methyl hydroxyl group, so it will not react with alkaline aquacidin. So you must remember that ethanoic acid, though there is CH3CO group is present, but since it is ethanoic acid and not methyl ketone or methyl hydroxyl, so it did not react with alkaline aquacidin. Then for Y, we can see that CH3CO group is present, and this is methyl ketone. So it would react with alkaline aquacidin and a yellow precipitate is formed. Then for Z, here we can see that there is methyl hydro. This is also a methyl ketone, that is CH3CO group is present. So it would form a yellow precipitate with alkaline aquacidin. 2,4-DNPH. 2,4-DNPH reacts with aldehyde and ketone. So for Y and Z, here we can see that a ketone group is present and an aldehyde group is present. So with 2,4-DNPH, an orange precipitate is formed. Then with tolerance reagent is an oxidizing agent and it would react with aldehyde and not ketone. So Z contains aldehyde group but Y contains ketone, so it does not react with tolerance reagent. So Y does not react with tolerance reagent, but since Z contains aldehyde group, so it would react with tolerance reagent to form a silver mirror. Consider an equation for the reaction of Z with NaBH4. So Z is an aldehyde, that is CH3COH group is present. So CH3COH group is present. So aldehyde reacts with NaBH4 and use hydrogen to represent an atom of hydrogen from the reducing agent. So aldehyde reacts with this reducing agent, that is NaBH4 is represented by this symbol. So aldehyde reacts with reducing agent to form ethanol. Since there is 2 carbon aldehyde, so it would be converted to ethanol. NaBiO3 can be used to determine the concentration of Mn2 plus aqueous. The ionic equation for the reaction is shown in equation 2. So this is the ionic equation for this reaction, and we need to find the concentration of Mn2 plus. That is concentration of Mn2 plus concentration. A student uses the following procedure in an experiment. Add 100 cm cube of the saturated solution of Mn2 plus in the volumetric flask. Now this 100 cm cube is the saturated solution. Then add distilled water to the flask to make 1 dm cube of dilute solution. So in this 100 cm cube, he further adds distilled water to make 1 dm cube or 1000 cm cube of solution, and this solution is dilute solution. Titrate a 25 cm cube of the sample of diluted solution with 0.1 mole per dm cube of NaBiO3. Now from this dilute solution, he uses 25 cm cube to react with NaBiO3, and we have given the concentration of NaBiO3. 25 cm cube of the sample of diluted solution of Mn2 plus reacts completely with exactly this much volume and concentration of NaBiO3. So 25 cm cube of the diluted solution reacts with this much volume and concentration of NaBiO3. Now we need to find the concentration of Mn2 plus in the saturated solution. So we need to find the concentration in the saturated solution, that means in 100 cm cube of the saturated solution. So to find the concentration in the saturated solution, first of all we need to find the number of moles of NaBiO3. So what is the number of moles? Number of moles is equal to volume into concentration, and we have given the volume and its concentration. So this is the number of moles. And so what is the number of moles of Mn2 plus? So as the ratio of NaBiO3, that is BiO3 minus, and Mn2 plus is 2:5. That means for 5 moles of BiO3 we get this much volume. So for 2 moles of Mn2 plus, that is the number for this much mole of Mn2 plus, we get this much mole. So according to the balance equation, we get this much mole of Mn2 plus. Then, and we know that this much mole is for 25 cm cube, since we use 25 cm cube of dilute solution. So for 25 cm cube of the dilute solution, we get this much mole. So for 101 dm cube or for 1000 cm cube of the dilute solution, since we have used 25 cm cube of the dilute solution, we get this much mole. But for 1000 cm cube, we need to divide the mole by 25 into 1000 to get the number of moles for 1000 cm cube. And we know that in 1000 cm cube of dilute solution, now this 1000 cm cube is for dilute solution and this 100 cm cube is for saturated solution. And since the difference between the dilute solution, that is this dilute solution, and this concentrated solution is only the difference in water, and so we can ignore this, and so 100 cm cube of the saturated solution contains the same number of moles of Mn2 plus, that is the same number of moles of Mn2 plus as 1 dm cube of 1 or 1000 cm cube of dilute solution. So for 100 cm cube of saturated solution, we get the same number of moles of Mn2 plus as for 1 dm cube of or 1000 cm cube of the dilute solution. That means the number of moles in the dilute solution in 100 cm cube 1000 cm cube is same as 100 cm cube of saturated solution. So for 1000 cm cube of dilute solution, 1000 cm cube of dilute solution, we get this much mole. So this mole is same as in saturated solution of 100 cm cube. So for 100 cm cube, we get the same number of moles, that is this number of moles. So this is the number of moles, and we need to find the concentration in the saturated solution. So what is the concentration? Concentration is the number of moles divided by volume, that is 100 cm cube. So, and we need to must convert it to dm cube by dividing with 1000. So we get the concentration as 0.344 mole per dm cube. Question number 2. Chlorine reacts with many elements and compounds to form chlorides. Table 2.1 shows the information about some chlorides of period 3 elements. So sodium, magnesium and silicon. Formula of chloride. So sodium chloride NaCl, magnesium chloride MgCl2, silicon chloride SiCl4. Then the structure of the chloride. So sodium chloride is an ionic compound, so it is a giant ionic structure. Then magnesium chloride is also an ionic compound, so it has a giant ionic structure. But silicon chloride is a simple molecular structure, and since it is a simple molecular structure, so it exists as a liquid at room temperature and pressure. So bonding, sodium chloride has ionic bonding, magnesium chloride has ionic bonding, and silicon chloride has covalent bonding. And what is the pH when added to water? So NaCl does not react with water and it only dissolves in water. So NaCl dissolves in water to form Na plus and Cl minus ion, and so it does not react with water, so the pH remains the same as the pH of water, that is 7. And MgCl2 also dissolves in water to form Mg plus, Mg2 plus and Cl minus ion, but some of it reacts with water, so the pH slightly decreases to 6.2 or 6.5. Then for aluminum chloride, that is AlCl3, the pH of the solution is 3, but after aluminum, that is silicon phosphorus sulfur, the pH is 2 due to the presence of HCl. That is silicon chloride reacts with water to form silicon oxide, that is SiO2 and HCl, that is HCl. Then in part B, when chlorine reacts with cold sodium hydroxide, so the reaction of chlorine with cold sodium hydroxide is sodium hydroxide reacts with chlorine to form NaCl, NaClO and H2O. Chlorine is both oxidized and reduced. The products of the reaction is NaCl and G. So G is the NaClO. State the type of redox reaction in which the same species is both oxidized and reduced. So the same species is both oxidized and reduced in a disproportionation reaction. Then identify G. So after writing the equation, we get the G as NaClO. So NaClO. Write an equation for the reaction of chlorine with hot sodium hydroxide. So chlorine reacts with hot sodium hydroxide to form NaCl, NaClO3 plus H2O. And if we just balance, then there would be 6 NaOH, 3 chlorine, 5 NaCl and 3 moles of water. 4. Describe fully what is observed when silver nitrate is added to aqueous solution of sodium chloride, followed by dilute aqueous ammonia. So silver nitrate reacts with sodium chloride to form silver chloride, and as we know that silver chloride forms a white precipitate, and silver bromide forms a cream precipitate, and silver iodide forms a yellow precipitate. So for silver chloride, white precipitate is formed that dissolves in aqueous ammonia to form solution, and the reaction is silver nitrate plus sodium chloride, sodium nitrate plus silver chloride, and silver chloride is a precipitate. And when silver chloride reacts with aqueous ammonia, this complex ion is formed, that is AgNH3 2 plus Cl minus. Then in part C, an excess of chlorine reacts with phosphorus to form PCl5. PCl5 is a simple molecule in the gas phase. It also exists as a solid as two ions, PCl4 and PCl6. Complete the table 2.2 to identify the shape of each of these species. So PCl5, this is P, and this is one chlorine, another chlorine, then this is another chlorine, and these two are chlorine, that is Cl and the rest of the Cl. So this angle is 90 degree and this angle is 120 degree, and the structure is trigonal bipyramidal. So the shape is trigonal bipyramidal for PCl4, since PCl4, so P and Cl4, so this is tetrahedral, and for PCl6 the shape would be octahedral, that is PCl6, 1 2 and this is 6, so 1 2 3 4 5 6, so this is an octahedral shape and the angle is 90 degree. And for this angle, the angle would be, for tetrahedral the angle would be 109.5. Then PCl5 reacts with J to form H3PO4. So PCl5 reacts with J to form H3PO4. Identify J. So PCl5 reacts with water to form H3PO4 and HCl. So J would be water and H3PO4 is formed, and this reaction is T. Chlorine reacts readily with propene to form K, 1,2-dichloropropane. So chlorine reacts with propene and the double bond breaks, that is the double bond breaks and two chlorine atoms are attached on either side of the double bond, that is this structure. Then complete 2.2, figure 2.2 to show the mechanism for the reaction of chlorine with propene in reaction 1. So, and for the structure of K, there is CH3 group is attached, then CH, Cl, CH2 and Cl group is attached. So this is the structure of K. Then include charges, dipoles and lone pair of electrons and Caillie arrows as appropriate. So for the mechanism for the reaction, that is this reaction. So for the first reaction, that is chlorine with propene, that is METH ETH probe. So propane reacts with chlorine, and this is delta positive and delta negative. Then double bond attacks this delta positive and this double bond breaks. So now the structure would be that this is the structure. Here is H, and so the structure would be that H, then H, then Cl, and this is positive charge and Cl is negative charge with lone pair of electrons. Now this lone pair of electrons can further attack to this positive charge to form this molecule, and this is an SN2 reaction, SN2, since this is a primary or secondary carbocation. Part 2. Identify the reagent and the condition for reaction 2. So for reaction 2, we can see that this molecule, that is this molecule, is converted to this molecule containing the double bond. So here hydrogen is removed, and from this carbon chlorine is removed, and the double bond is formed. So this is an example of elimination reaction. So elimination reaction occurs in presence of sodium hydroxide in ethanol or ethanolic sodium hydroxide and in presence of heat. So this reaction occurs in presence of ethanolic sodium hydroxide, and if suppose there is aqueous sodium hydroxide, then nucleophilic substitution reaction occurs. But for now, this is elimination reaction. Draw one repeat unit of the addition polymer forms from L. So what is the structure of L? So this is L. So for L, this carbon atom is double bonded to the next carbon atom, and one methyl group and one Cl is present. So carbon atom is bonded to another carbon atom, methyl group and Cl is present, and this is the double bond. So as it is an addition polymer, so the double bond breaks, that is the double bond breaks, and here there is CH2 group that is not shown. So the double bond breaks and the hand opens. So this is the one repeat unit, and this is the structure of the addition polymer. Number 3. Nitrogen is generally unreactive molecule, but it does react under certain conditions. Give 2 reasons to explain the lack of reactivity of nitrogen. So nitrogen exists as this molecule, and here we can see that the triple bond is present. So nitrogen to nitrogen triple bond is present, that is difficult to break since it has high activation energy, and due to this high activation energy, the nitrogen molecule is non-polar. So it is non-polar. Then in part B, nitrogen can react with oxygen in internal combustion engine to form a mixture of nitrogen monoxide and nitrogen dioxide. So nitrogen first of all reacts with oxygen to form nitrogen monoxide and nitrogen dioxide. So write an equation to show the formation of nitrogen monoxide and nitrogen dioxide in reaction 1. So nitrogen plus oxygen, nitrogen monoxide and nitrogen dioxide. So as there are 3 moles of oxygen, so 3 by 2 to balance the number of moles of oxygen. Then give the formula of the product of reaction 2. So from reaction 2, nitrogen dioxide reacts with water to form nitric acid that causes acid rain, that is HNO3, and nitrogen monoxide is formed. So this is the equation for this reaction, and to balance this equation, here there is 2 hydrogen, so we place a 2, then 2 plus 1, 2 and plus 1, 3, so 3 nitrogen, so 3. So nitrogen is balanced, hydrogen is balanced, and oxygen, 6 oxygen plus 1, 7 oxygen, so here is also 7 oxygen. So this equation is balanced, and the product is nitric acid plus nitrogen monoxide. Then state 1 environmental consequence of reaction 3. So nitrogen dioxide reacts with unburned hydrocarbon to form PAN that causes photochemical smoke. So the environmental consequence would be the Haber process involves the reaction of nitrogen with hydrogen to form ammonia. So nitrogen reacts with hydrogen to form ammonium. A catalyst is used which allows the process to be carried out at a lower temperature and pressure. Use the information in C to complete table 3.1. So this is a table and we need to complete this. So what is the information in C? So this is the information in C. Okay. So for this reaction, we need to find the enthalpy change of formation. So enthalpy change of formation is the energy change when one mole of a compound is formed from its elements under standard state. So nitrogen reacts with hydrogen to form ammonium. So initially it is nitrogen in gaseous state and hydrogen in gaseous state. And for the formation, we can see that the nitrogen remains the same and hydrogen also remains the same. That is, both are in gaseous state and they remains the same. So nitrogen 2 in gaseous state, so nitrogen in gaseous state, hydrogen in gaseous state. So since there is no overall change, so the enthalpy change of formation is 0, since nothing is really formed. So enthalpy change of formation is 0, and for the enthalpy change of formation of ammonia, we can see that 2 moles of ammonia is formed. So for enthalpy change of formation, that is the enthalpy change of formation is the energy change when 1 mole of compound is formed. So 1 mole of a compound is formed from its elements under standard states. So for 1 mole of a compound, the value is divided by 2, that is this value is divided by 2 to get an answer that is negative 46. So the enthalpy change of formation of ammonia is negative 46. To explain how the presence of catalyst affects the reaction. So catalyst increases the rate of the reaction by lowering the activation energy and by providing alternative pathways, and it has no effect on the position of equilibrium. Also, the catalyst does not use up at the end of the reaction. So catalyst increases the rate of the reaction by lowering the activation energy and by providing alternative pathways, and it has no effect on the position of equilibrium and it is not used up at the end of the reaction. State and explain the effect, if any, on the rate of Haber process as the pressure is lowered. So as the pressure is decreased, that is pressure is decreased, so decreasing the pressure will shift the equilibrium on the side while the number of moles are more. So as we can see that the number of moles of gas on the product side is 2 and for the reactant side the number of moles is 4. So since the number of moles is more in the reactant side, so decreasing the pressure will shift the equilibrium on the side while the number of moles are more. So but we need to find the rate of the reaction. So what happens to the rate? So since pressure is decreased, so the rate of the reaction is decreased. So pressure is decreased, so the rate of the reaction is decreased as the frequency of the effective collision between the reactant molecules decreases. Since pressure is decreased, so the rate of the reaction also decreases as the frequency of the effective collision between the reactant molecules decreases due to less number of molecules present or less pressure or more distance between the particles. So the rate of the reaction is decreased as the frequency of the effective collision between the reactant molecules decreases, and it measures about the rate and not the position of equilibrium. Less molecules are closer to one another, so the pressure decreases, so the rate of the reaction also decreases because the molecules are further apart. Then in part D, N2F2 molecule has a double covalent bond between nitrogen atoms. So between the nitrogen atoms, the double covalent bond is present. That is, from each nitrogen atom, 2 electrons is shared. So from each nitrogen atom, 2 electrons is shared. Then this consists of a sigma bond and a pi bond. Complete figure 3.2 to show the dot and cross diagram of N2F2 show outer electrons only. For the outer electrons, as fluorine is in group 7, so it has 7 outer electrons, that is 1, 2, 3, 4, 5, 6 and 7. Then 1, 2, 3, 4, 5, 6 and 7. And as we know that nitrogen contains 5 outer electrons, so 2 of them are shared between these 2 nitrogen, and to get an octet electronic configuration, it shares 1 electrons with this fluorine to make the fluorine an octet electronic configuration, and 2 are the lone pairs, that is 1, 2, 3, 4, 5. So 5 electron is involved. Then for this nitrogen, 2 electrons is shared between the 2 nitrogen and 1 nitrogen is shared between the fluorine, and 2 nitrogen is a lone 2 electron is the lone pair or lone pair of electrons. So this is the structure. Then deduce the hybridization of nitrogen in N2F2. Since we can see that the double covalent bond is present, that is between nitrogen atoms double covalent bond is present. So double covalent bond is present, so this is sp2 hybridized. Also, as nitrogen is attached to two atoms, that is 1 2 atoms and one lone pair of electron is present, so 3, that means sp2 hybridized. So sp2 hybridized, that is the number of atoms attached plus number of lone pairs. Is the hybridization. So for nitrogen 2 atoms are attached and one lone pair, so in total there is 2 atoms and one lone pair, so 3, that is sp2 hybridized. So nitrogen is sp2 hybridized. In part 3, draw a diagram to show the pi bond. So pi bond, so sigma bond is this bond, that is for by head-on overlap. So by head-on overlap sigma bond is formed, that is this sigma bond, and this is also sigma bond. But for pi bond is the sideways overlap, that is this sideways overlap or this bonding. So we need to show the pi bond and describe how it forms. So for N2F2, so N2F2, so first of all we draw the single bond, that is a sigma bond, then this is the pi bond, that is represented by the symbol or this drawing. So how pi bond is formed? Pi bond is formed by the sideways overlap of p orbitals. So sideways overlap of p orbitals forms the pi bond. Number 4, compound S is used in food coloring. A possible synthesis of S is shown in figure 1.1. So P, that is 2 carbon-carbon double bond is present and CH3 group is attached and one hydrogen is attached. Then okay, so this is the structure and this is the diagram shown. PQRS are stereoisomers. Complete table 4.1 to identifying with a tick the type of stereoisomers that each molecule shows. So we need to just place a tick. So type of stereoisomer shown by Q, and you must remember that here we need to just place a tick and we do not need to place a cross. So we do not need to place the crosses and we just only need to place the ticks. Okay, so for the structure of P, first of all, if we just convert the skeletal formula to the displays of the structure formula, then this is the structure of P. And for Q, P reacts with HBr, and due to the reaction the double bond is broken or hydrogen is attached to one carbon and Br is attached to the another carbon. Then it reacts with KCN in ethanol or NaCN in ethanol to form CH3, that is CH3, CH2, CH, CN, CH3, that is this Br is replaced by CN, CN is replaced by Br. Since this is a nucleophilic this is an elimination reaction, nucleophilic substitution reaction. So here Br is just replaced by Cn to form this structure, that is I have drawn. So this is an example of nucleophilic substitution reaction, that is Br nucleophile is substituted by Cn nucleophile. Then R reacts with hydrogen ion in aqueous, that means acidic hydrolysis occurs. Since it is aqueous, so water is present and hydrogen ion, so acidic hydrolysis occurs and Cn is converted to carboxylic acid, that is this structure. And for PQRS, we need to show that which contains geometrical isomerism. Now geometrical isomerism or cis-trans isomers only occur when carbon-carbon double bond is present. So for structure P, we can see that the carbon-carbon double bond is present, and here we can see that each carbon atom is attached to two different groups, so cis-trans isomers would occur. So here geometrical isomer or cis-trans isomer occurs. Then for Q, no double bond is present, so no cis-trans isomer is present. Also for R, there is no double bond present, and for S, there is no double bond present, so no cis-trans isomerism is present. And as there is nothing is present, so you do not need to give a cross, since we need to just give a tick. And if it is not present, then leave this as a blank. Then for optical isomerism, for optical isomerism, the carbon atom must contain 4 different groups, or 4 different groups are attached to the carbon atom. So here we can see that for none of the carbon atom is attached to 4 different groups. Then for Q, we can see that this carbon atom is attached to 2 hydrogen, so 2 same groups are attached. So this would not show a cis-trans isomerism, optical isomerism. But for this carbon, here we can see that this carbon is attached to 4 different groups, so this would show a optical isomerism that is already given. Then for R, we can see that this carbon atom is attached to 4 different groups, that is hydrogen, H, cyanide, CH3 and CH3CH2. So this would show optical isomerism. Then for S, for the structure of S, we can see that this carbon atom is attached to 4 different groups, so this would also show optical isomerism. B part 1, give the structural formula of Q. So what is Q? So Q contains CH3, CH2, so CH3, CH2, then C, CHBr, CH3, so CHBr, CH3. So this is the structural formula for Q. Then name the mechanism in reaction 2. So for the reaction 2, we can see that KCN in ethanol is used, so nucleophilic substitution occurs, and Br nucleophile is substituted by Cn nucleophile. So this is an example of nucleophilic substitution reaction. Then complete the equation for reaction 3. R is represented as this formula. So R, so what is reaction 3? R is converted to S, and this Cn is converted to COOH group, that is acidic hydrolysis occurs, so hydrogen ion, and as acidic hydrolysis occurs, so hydrolysis occurs, that means water is also present. So in presence of water and hydrogen ion, S is formed. So S contains 1, 2, 3, 4 carbon, 9 hydrogen, and COOH group is present. So 4 carbon, 9 hydrogen, and COOH group is present. So this is R, this is S, and this is R, and acidic hydrolysis occurs. So as S is formed, ammonium ion is formed. Since hydrogen ion is present, so ammonium ion is formed, and if suppose there is HCl or hydrochloric acid is present, then it will be ammonium chloride. But for now, since hydrogen ion is present, so ammonium ion is formed. Then for part C, compounds S and T react to form organic compound U, which has a single functional group. So S reacts with T to form a compound U with single functional group. That is, S contains carboxylic acid and single functional group, that means carboxylic acid reacts with alcohol, that is COH group. Carboxylic acid reacts with alcohol to form an ester. So this is a ester that is formed in water. Now use the data in table 4.2, that is this data, to show that U contains 7 carbon atoms. So from this data, to calculate the number of carbon atoms, we know that N is equal to 100 by 1.1 into M plus 1 peak by M plus peak. So 100 by 1.1, M plus 1 peak divided by M plus peak. So we get the number of carbon atoms as 7. Then this figure shows the infrared spectrum of U, and from this infrared spectrum, first of all, here we have given the data. Then from this infrared spectrum, we can see that no broad peak is present. So that means OH group is not present. That means U must be an ester. Then here we can see that there is a sharp peak present, and this is represented by 15, 16, 17. So 1720. So 1720, that is CO, that is ester. So there must be an ester present, that is COO. So carboxylic acid reacts with alcohol to form this ester, and as we can see that from the spectrum, no OH group is present, and so it must be an ester. So use figure 4.2 and table 4.3, that is the above figure and this table, to identify the functional group in U. So for the functional group is in U, we can see that the only peak that is present is CO peak is present. Also we can see that here there is also a peak is present, and this peak is 11, 12. So it is between 11 to 13, that is this is CO group is present, that is 1040 to 1300. So this is CO group is present, that is CO, and CO group is present, that is C double bond O and C single bond O is present. So it must be an ester. That is CO group is present. Also here we can see that CO, that is single bond O, C single bond O is present, that is CO group is also present, that is CO group is present. So it must be an ester, and the absorption between 17 to 1750, that is the presence of C double bond O, and 1040 to 1300, that is absorption between 1040 to 1300, implies that CO is also present. So COO, that is ester. Then T also has a single functional group. Use the information in C1 and C2 to identify T and U. So this is the equation. So this equation we have given, S reacts with T to form U and water. So we know that in U, CO is present, that means it is an ester, and S, that is carboxylic acid, reacts with alcohol to form an ester. So we need to find the structure of T and U. So for the structure of T and U, so S reacts with T to form U, that is the ester that I have just shown. So this is the ester. So U is an ester. So carboxylic acid, that is S, reacts with T to form the ester, and it mentions that T has a single functional group, and we know that carboxylic acid reacts with alcohol to form an ester. So T must contain an alcohol functional group, that is COH group is present. And what type of alcohol, or it is methanol, ethanol, propanol, or butanol, we can identify this by, as we know that initially we have given that U contains 7 carbon atoms. So U must contain 7 carbon atom, that is U is the ester. So ester contains 7 carbon atom, and for this carboxylic acid, that is S, we can see that for the structure of S, that is 1 2 3 4 5. So S contains 5 carbon atoms, and the rest of the 2 carbon atom is from the alcohol. So T is the alcohol, so it contains 2 carbon atom, that is ethanol, that is CH3 CH2OH. So T is an ethanol, and they both react, that is this carboxylic acid reacts with alcohol, and here from carboxylic acid OH group is removed, and from alcohol H is removed, and here bonding is formed, that is this bonding, and this is the structure of U. So the rest of the structure remains the same, and just there is a bond between this carboxylic acid and alcohol to form this ester, that is COO group. So this is the structure of U, and this is T.